Hey everyone, and welcome. Today, we're going to get our hands dirty. Well, metaphorically anyway. We've got this blueprint for a computer network, but right now, it's just a bunch of disconnected boxes on a diagram. Our job is to turn this drawing into a real, living, breathing network, one cable at a time. Let's jump in.
So here's the big question, right? Imagine you're handed a box full of different cables, and you're in a room with PCs, servers, and switches. How in the world do you connect everything so that it actually works? It's kind of like a high-tech jigsaw puzzle. If you pick the wrong piece for even one connection, believe me, the whole thing just won't come together.
To solve this puzzle, we've got a clear 5-step game plan. First, we're going to get to know our tools, the cables themselves. Then, we'll start small, connecting our end devices, like PCs. After that, we'll link all the switches together, connect them up to the routers, and finally, we'll tackle the biggest challenge of all, bridging those long-distance connections. It's a logical build from the inside out.
All right, first things first. Before we can start plugging anything in, we've got to understand the tools we're working with. Choosing the right cable is basically everything in this scenario, so let's get familiar with our options.
In our toolkit, we've got three main players. There's your standard copper straight-through cable, its slightly more complicated cousin, the copper crossover, and then the long-distance champion, fiber optic cable. Each one has a very specific job, and knowing when to use which is the real secret to building a successful network.
Now, for this whole exercise, there's one really important rule we have to play by. See, most modern network gear has this clever feature that automatically figures out the cable type for you. We are turning that off. Why? Because it forces us to think like old-school network engineers and manually, deliberately choose the correct cable for every single connection. No shortcuts allowed.
Okay, it's time to make our first connections. We're going to start with the end devices, the PCs and the server, and plug them into their local switches. This is where we'll see the first, and honestly, the most fundamental rule of network cabling come into play.
So, why all the fuss about cable types? It all comes down to the wiring inside. Take a look here. A PC is built to talk or transmit data on one pair of wires, pins 1 and 2, and it listens or receives data on another pair, pins 3 and 6. A switch is engineered to be the perfect opposite. It listens on 1 and 2 and talks on 3 and 6. It's the perfect setup for a smooth, two-way conversation.
And that is exactly where our first tool comes in, the straight-through cable. It does precisely what the name says. It connects pin 1 on one end to pin 1 on the other, pin 2 to pin 2, and so on. Since the PC and the switch are already wired as opposites, this simple direct connection is all you need. The PC's talking pins connect right to the switch's listening pins. Perfect.
So by applying that one simple rule, we can start plugging things in. We'll grab a straight-through cable for our first PC and connect it to its switch. Then the second PC to its switch, and the third one. And finally, we connect the server. And just like that, all of our end devices are officially on the network. But trust me, that was the easy part. Okay, so our PCs are connected, but right now they can only talk to their own local switch. If we want them to talk to each other, we've got to connect all the switches together. And this is where things get a little tricky, because now we're trying to connect two identical devices.
You see, if we tried to use a simple straight-through cable here, we'd run into a huge problem. As it says here, the transmit pins on one switch would connect directly to the transmit pins on the other. It'd be like two people trying to talk at the exact same time. Nobody's listening. Data traffic just grinds to a halt.
The solution to this problem is our second tool, the crossover cable. And it is ingeniously simple. Inside the cable, it physically crosses the wires, so the talking pins on one end get connected to the listening pins on the other. It basically forces two identical devices to have a proper conversation. It's a really clever fix.
So now, with our crossover cables at the ready, we can start linking our whole network together. We connect the first set of switches, then the next, and so on, creating a chain of communication all the way across our local network. With that done, our switch infrastructure is complete. Now we need to get this whole system connected to the outside world. And for that, we need the routers.
Our network of switches is now all linked up, so the next logical step is to connect this entire local system up to the routers, which are our gateways to other networks.
And here's the cool part. Connecting a switch to a router is surprisingly simple. We just have to remember one key detail. For cabling purposes, a router is wired just like a PC. That means we're back to connecting two different types of devices again. And what do we use for that? You got it. We're back to our trusty, basic straight-through cable.
So we just apply that rule. We run our straight-through cables from our main switches right over to the routers. And with those connections made, our local area network is fully built out. In theory, every single device can now talk to every other device through this web of switches and routers.
And now we've reached the final, and I think the most interesting part of this puzzle. We have to connect the routers to each other. But here, a brand new factor comes into play that we haven't had to think about until now: distance.
See, a standard copper network cable has a physical limit. Once you go past about 100 meters, or around 328 feet, the signal just gets too weak and unreliable. So this 100-meter mark suddenly becomes a critical new piece of information in our decision-making process.
Let's apply this to our first router-to-router connection. The distance is only 50 meters, which is safely within that 100-meter copper limit. And since we're connecting two similar devices to routers, we know we need a crossover cable. So a simple copper crossover is the perfect tool for the job. Easy enough.
But what happens when we need to go further than 100 meters? For that, we have to ditch copper and start using light itself with fiber optic cables. The easy way to think about it is this. Multimode fiber is great for medium distances, like connecting buildings across a campus. It's good for up to about 550 meters. Single-mode fiber is the heavy hitter, designed for connecting cities, capable of sending a signal for kilometers and kilometers without losing any strength.
And this table right here lays out our final decisions perfectly. The 250-meter run between routers, that's way too far for copper, but it's perfect for multi-mode fiber. And that massive 3-kilometer gap, well, that is a job that only single-mode fiber can handle. In the end, for these long-haul connections, it's the distance that dictates the technology we have to use.
And just like that, we're done. Every single connection has been made using the correct cable, all based on the types of devices and the distances between them. Our abstract blueprint on a page is now a fully connected, physical network. Job well done.
But, this brings up a really fascinating question. The physical links are all there. The highways have been built, but there's no traffic on them yet. The devices are all connected, but they don't know how to speak the same language or follow the same rules of the road. So how do we get them to actually start talking to each other? Well, that is a story for another time.